Hi, and this is going to be our final video for Year 1 integration. So what we've looked at in the previous videos is definite integrals, area under curves. We're now going to finish off with looking at how we find the area between two curves. So on we go. So here we go, we've got straight into an example. We've got to find the area enclosed between the curve y equals x, which is clearly our red line here, and we've got the straight line y equals 3x plus 4, which is the blue one here. Okay, first things first, we need to figure out if we're going to be integrating, we need to know the limits, so we need to know where do these two lines meet. So we can do that by just putting the two things equal to each other and solving the quadratic. And there we go, we've got x equals minus 1 and 4. And while I'm at it, I'm going to work out the y values as well, and you'll see the reason for that in a second. So we've got this point here, which is at minus 1, 1, and we've got this point up here, which is at 4, 16. Okay, so we figured out where our limits are going to be between our x values. So now we need to have a little look at how we're going to find out what the value of that blue area is going to be. Now, to do that, we need to look at it and say, well, the blue area that I'm interested in there is going to be the area underneath the blue line. So this entire shape here. And then we've got to take away from it the bit that's white on here. I've coloured it yellow on my diagram here. So I need this kind of beige area, take away the bright yellow area, and that will leave us everything, the blue bit that's kind of sandwiched in between the two. So what we're going to have to do is work out these two areas separately and then do a subtraction at the end. So, and this is where I decided I needed those values, because if we have a look at our kind of beige coloured area under the blue line here, that is basically just a trapezium. So one way to do it would be just to work it out as the area of a trapezium, and there we've got our y coordinates, 1 and 16 being the two heights of our two parallel sides on our trapezium. So we can just chuck that in, it's trapezium, there's our formula, and so we know that our beige area there is 42.5 square units. Let's now do the yellow bit. So we've just got to integrate underneath the curve y equals x squared between the limits of 4 and minus 1. And that's a fairly straightforward process. And we've got a value of 21 and 2/3. And so all that remains to be done now is say, well, you know, the beige bit is 42.5. There it is. The bright yellow bit is that 21 and 2/3. And then the final step is just do the subtraction. And so that leaves us with our blue area, which is 20 and 5/6 units squared. Now, we're going to do exactly the same thing again. You might be thinking, well, why would we bother? We've already solved it, but I'm just going to do it, showing you a different way to do it. And we did it in the first instance by separating it out into two completely separate calculations and then the subtraction. Another way to do it would be to do it as in a single go. And we say, well, the area that we need is the area under the top curve, i.e. at this point here, kind of the blue line is above the red line, so it's the blue line that's the top curve. Take away the area under the bottom curve. That's what we did on the last slide. But what I'm going to do is write that as a single integral. So in both cases, our limits were between x equals 4 and x equals minus 1. So we've just got to do the difference between those two things. So the area under the top curve, which is that one, take away the area under the bottom curve. So now let's just take this and integrate this as one thing here. So we've got 3x squared over 2 plus 4x minus the integral of x squared, which is there. Plug in the limits. And then when you work that all out, it turns out, no surprise, it's exactly the same answer. Now, you might be looking at this one thinking, well, why would you do it as two separate bits? The only reason for doing that would be you've got to be a bit careful, because here, if you've got a more complex expression here for your bottom curve, you've got to be a little bit careful with kind of the subtractions if you've got any minuses in there. So kind of doing it as two separate regions does get rid of that issue of minusing, but long story short, it's basically just whichever you prefer to do. Both will work quite happily, as you've seen. Okay, so let's go on to something that's looking a lot more horrible. This one's a real nasty one. We've got a lot of stuff to think about. So we want the blue area there, and the first thing to think about is, let's say, well, the blue region here is not underneath the curve. The area, if we just integrated underneath our red curve, underneath our cubic curve, would be these white bits here. We want this area above the curve here. So we're going to have to think a little bit more carefully about what we're doing. So we've got the tangent to the curve, the blue line here, And clearly, again, same as before, we're going to need limits. We're going to need to know what's the x-coordinate here, what is the x-coordinate here. So let's start off by figuring out the tangent to the curve at that point there. So we want to know about a turning point. Going back to our work on differentiation, we know that the turning point is when dy dx equals 0. So let's do some differentiating. Stick it equal to 0, so dy dx is 0. So our x-coordinate here is going to come from the solution to this equation here. So although this video is about integrating, we've ended up having to do some differentiating. So away we go, solve the quadratic, and we get x equals 3 and minus 1. And clearly on our diagram here, this point here is x equals minus 1. Okay, so that's that bit sorted. And again, I'm going to work out the y value when x equals minus 1. And again, you'll see the reason for that in a minute. And it might be you've already guessed why I'm going to do that. So chuck x equals minus 1. Okay, being very careful, we've got to plug it back into this equation up here to get the y coordinate. Plug it in, and we get a y value of 33. So the coordinate at this point here is minus 1, 33. So that's the first bit of work done. We've found the first limit. We've got this value which we're going to need later. Clearly we're now going to need this point here. So the next job to do is say, well, okay, what is going to be the x-coordinate at that point there? And that's going to be where the blue line and the red line intersect, which is going to be at the solution to that equation there, where y is 33. That's why we needed it. So get that equal to 0. Now, as it turns out, we already know kind of the one solution, because again, this is a point where the blue line and the curve intersect. So we know that x equals minus 1 will be a solution to this equation. So we can use a bit of factor theorem. So, well, x plus 1 is a factor of that. Do some plugging, however you choose to do that, either division, or you can do it by inspection, or alternatively, you know what, I keep forgetting, we've got calculators that will solve a cubic for us, so you could just get that from your calculator. But long story short, we end up with solving the equation, and that gives us the value of x equals 5 at this point here, where the red curve and the blue line intersect. So now what we've done here, this entire slide here was just kind of preparatory work, getting ready to do the integration. Basically, it was all about finding those two limits. So that says a lot of work to do on this question. So on we go. We've got those two limits. We've now got to figure out, okay, well, how do we find the area of the blue curve? Well, essentially, the area of the blue curve is going to be the area of that yellow rectangle there, which is, again, it's got a value of 6. That distance there is 30, so that area there is 198. And we've got to take away from it the area of the that's underneath the curve. And if we do that 198, take away a yellow bit, that's going to leave us with the blue area, which we need. So now we need the area under the curve, which we're going to get from integrating between 5 and 1. Do the integrating, plug in the limits, and out pops our value. So it turns out this kind of honky yellow colour here has got a value of 90 square units. So all that remains to be done now is work out the area of the blue bit, which we're going to do from our subtraction. So we've got our area of the rectangle. I'm just going to redraw it out here. Our area of our rectangle here that I'm tracing out was 198. Take away the beige bit, and the blue bit that we're left behind is 108 square units. Jobs are done. So now if you've worked through all that series of video, we've basically dealt with everything you need to know about year 1 integration. Obviously year 2 integration is a whole other matter, and it does go absolutely bonkers in year 2, but you know what, let's worry about that when we get there.